Hi, I'm going to do a quick video about continuous random variables that we're going to talk about in Module 1. So you can go through the PowerPoint and it'll highlight what we've been doing, a lot about the probability distribution function and the cumulative distribution function. But I'm going to go ahead and start talking about distributions themselves. For this chapter, we're going to talk about uniform distribution. And if you look at the picture, it's almost like a rectangle. If I start at 2 and I go to right before 9, it means that all these numbers have the same height for the distribution. It kind of makes a rectangle. It can also make a square, but for this video and what we're going to look at in class, it'll always make a rectangle. Here's an example of an exponential distribution. As you can see, it starts to the left high and goes down. Just know that it will never, ever, ever touch the x-axis because it's potentially going to go on forever. Here's normal distribution, but we're not going to cover that till chapter 6. I just wanted to show it to you because I might reference it, but that's how it looks. So the first thing we're going to talk about is uniform distribution. And remember I told you all of this area in the rectangle equals 1. So you need to remember that this whole area that I'm showing my mouse in is 1. So here it goes from 0 to 20 on the x-axis. For y, it only goes 1 over 20 in height. That's because if I find the area of this rectangle, which is length times width, it's 1 over 20 times 20, which gives me 1. And here's how we write it. So I'm saying f of x, which is that y, equals 1 over 20 for 0 to 20. So if you can see that's what it looks like. All right. For the next example, I just did it and we showed you the same thing, basically talking about the same way that I just talked about on the last slide. Okay. And again, here's how I solved for the area. 20 times 1 over 20 gives you 1. Because as always, with a uniform distribution, this rectangle has to equal 1. So let's look at this. Suppose we want to find the area between f of x equals 1 over 20 and the x-axis where 0 is less than x is less than 2. So I'm looking for that little part in purple. So to do that, I do 2 minus 1 times 1 over 20 gives me 0.10. So the area or the probability of the area in purple is 0.10. And for this, remember, I can do area and probability being the same thing. So let's do it for this purple area here. We're not starting at 0, but I want to know for this area where f of x equals 1 over 20 and the x-axis where 4 is less than x is less than 15. So again, 15 minus 4 times 1 over 20 gives me 0.55. Again, remember, it doesn't have to start at 0. You're just looking at defined points. And because this is continuous data, we could have 4.5, 4.7. It doesn't have to be exact numbers that we saw with discrete. So let's do exact probabilities. So here, the exact probabilities that x equals 15. Well, that's going to be 0 because 15 is just a line. See, I didn't highlight anything here for purple. It's just saying, what is the probability that x will be 15? And that's 0. Because again, 15 is just a line, and I need to find the area. I need a rectangle or a box. I need an area to find. 15 is just a line, and I can't find the area of a line. Okay? So let's do another one. Okay? Let's go look at this one. All right, so for this one, the distribution is uniform because of the shape, and I want to know the probability of the area between 3 and 6. So with uniform distribution, you write it as x, and the tilde is, which means approximation. So x with the approximation of a uniform distribution where a is the lowest value and b is the highest. This is how you're going to write it. And then if you look here, this helps you solve it. The probability density formula is f of x, where 1 over b minus a for a is less than or equal to x is less than or equal to b. Okay, and this is the y-axis ending point, is that 1 over b minus a. You can find the mean, which is a plus b over 2, and the standard deviation is the square root of b minus a squared divided by 12. Let's do a few more examples. So here's one. The amount of time in minutes that a person must wait for a bus is uniformly distributed between 0 and 15 minutes. A, what is the probability that a person waits fewer than 12.5 minutes? B is, on the average, how long must a person wait? Find the mean and the standard deviation. There, that one, if you're looking for the average waiting time, you're looking for the mean. And then C, 90% of the time a person's weight must fall below what value? Okay, so let's go ahead and look at the first one. So this is how I would write it for X is the number of minutes a person must wait for a bus. A is 0, B is 15. So I write it as A approximates uniform distribution, 0, 15. So f of x equals 1 over 15 for 0 is less than x is less than 1. Okay? It should be 15 right there. I have a typo. Sorry about that. All right, so let's see. For the probability that a person waits fewer than 12.5 minutes. Okay, remember I'm looking from 0 to 12.5 because it says fewer. So it's going to be 12.5 minus 0 times 1 over 15, and I get 0.8333. Excuse me. The probability that a person waits fewer than 12.5 minutes is 0.8333. Right? So let's look at the next one. And here I drew it out for you so you could see it. All right? I need to find the mean and the standard deviation, and I did this here just by plugging in and solving. The mean is 7.5. The standard deviation is 4.3. All right, let's do that final one. That one's kind of a tough one. So it wants to know the amount of time a person must wait for a bus. So that 90% of the time a person waits falls below what value. Okay, so what I'm going to do is I'm just going to multiply it by 0.90. So I don't know what my base is, but I know what my percentage is. So I'm going to kind of solve it in reverse. So this time what I'm going to do is I know from 0 to 15 is the total wait time. So if I want 90% of that, all I do is 0.90 times 15, and that gives me 13.5. So 90% of the time, a person must wait at most 13.5 minutes. That's all that means. So if you see a percentile for this, all you do is do whatever the longest length is on the x-axis multiplied by your percentile change to a decimal. I think you should probably have seen this in class, so if you have any more questions, let me know.